Hi everyone, thank you for taking the time to listen to my talk where I will explore the connectedness and relations that we observe in the world around us. Talk about the world of mathematics, the world of art, music, or even nature. I think that exploring this intersection and connectedness might uncover some truths or mysteries about the nature of the universe. I will also be talking about a tool that we all share. It is a valuable and mysterious gift. It's called abstraction. This is what is also needed for mathematical thinking. Speaking of mathematics, when we think of school maths, we think of it as boring or useless. But this type of thinking is a daily necessary use. This thinking can allow us to look at different perspectives. It might seem like it takes us away from the normal life, but actually, because it is abstract, it can be applied to so many different situations and much more widely to a broader range of things. I will also explore category theory, which is the theory in maths that was developed in the 20th century. Category theory is about making connections between different ideas, which is really helpful in the efficiency of our understanding as humans. It is also about understanding structure more than problems and answers. It focuses on relationships, like in AI. In AI, when a computer doesn't know a word in a language, it finds the other words that are related to it, and therefore looks at other languages which finds that word and therefore is able to identify the word that it didn't know initially. Well, category theory also gives us different ways in which things can be the same or not, like humans. Nothing in the world is the same, but we can find similarities in different ways, differences in different ways. Category theory is often regarded as the mathematics of mathematics. Well, that's a lot of words, isn't it? But let's define mathematics. Mathematics is a study of things, a study of logical things, a logical study of logical things. So you can say that category theory is the logical study of the logical study of logical things. In reality, nothing is logical. Therefore, abstraction gives us the opportunity to forget the little details that prevent us from being logical and behaving logically. They enter an ideal world where everything obeys certain rules and cannot act otherwise. Well, you might ask, have we gone completely away from the real world? No, there are elements of the real world that can be understood logically. What we've got to be careful about is moving between and the process of going up and coming back again in different worlds. Pure mathematics is a theory of analogies, looking at similarities between situations that look different and spotting any patterns between them. Category theory helps us see more clearly and understand the structure in a more efficient way. To demonstrate this, I have drawn a little diagram on the board which might be difficult to read, but I will go through it. Here is two apples, and there is two oranges. What do they share? They share the number 2. This is how we get the concept of numbers, by the way. And apples and oranges are both subgroups of fruits. Fruits don't entail two chairs, so they're both under two things. And as we go higher, we reach higher levels of abstraction. There are two key things that we need to pay attention to. Key one, not to be as abstract as possible. It is to be it is to find a good level of abstraction for what you're trying to understand. And key two is to maintain the possibility of moving between the two levels. This is also about the flexibility of your perspectives. Category theory is about the flexibility of change in perspectives. You've got to be really adaptable to these different situations. Determining levels of abstraction eliminates a bit of ambiguity. This is why this process is illuminating. And to make it a bit more mathematical, I've got another example. If we look at here, 1 plus 2 and 2 plus 3 are both additions of two different things. Well, this addition is a binary operation. So we can say that this is a subgroup of A, and using a binary operation is connected to B. We can also get multiplication, division, or even subtraction. Also, we can get functions and matrices and so on until life. We can get anything using this using this different levels of abstraction. At the start of COVID, there were a lot of discussions whether COVID-19 is a seasonal flu. But using this diagram that we can see here, I am hoping to demonstrate the similarities and differences. COVID-19 and seasonal flu are both contagious viruses causing respiratory illness and fatalities. But the only difference that they had was that COVID-19 was new and it was less investigated. I don't think it's actually the same as anything else in real life. But if we remain flexible and respond to the changing circumstances, we can acknowledge that it is becoming more the same and that we can treat it more like we have done with seasonal flu. Drawing these pictures allows us to draw a framework for illuminating discussions. It can help us understand where the disagreement is, or at least agree on where the disagreement is. Putting things in context defines their character. For example, when humans are put in different social situations, they behave differently, like in a job, at school, or with their family or friends. Well, let us get more mathematical now. Let's define a circle. Circle is a shape with all points that are chosen at a fixed distance from a fixed reference point. That reference point is usually called as a center, and that fixed distance is the radius. But looking at it from a different perspective, in a different context, would be looking at it from a taxi cab distance. If we look at this shape, which looks like a diamond, we see that all the distances, if they are done by a taxi, would be the same, like at that one and like this one. We can see that these distances are the same, and I love that in this world that we just created, this would be a circle. This generalized distance and rule that I just applied into that is called a metric. We should think about what metrics we apply to people and think about and also take into account the obstructions that different people have fought against. This would allow us to understand their relationship with their own context that they were brought up and the things they went through. So this will give us more understanding of each other. Now let us explore some patterns and relationships. If we list the factors of 30, we would see 1, 2, 3, 5, 6, 10, 15 and 30. If we put 30 on top and ask which of the subsets of the factors of 30 are also made of two other factors of 30. 6 is, 10 is, 15 is. 6 is 2 times 3, 10 is 2 times 5, and 15 is 3 times 5. What they share and are in common are written by another arrow down. It's 2, 3, and 5. We can see that 6 and 15 share 3, 6 and 10 share 2, and 10 and 15 share 5. And at the end, these things share only 1 as their factor. Well, if you're a mathematician, you would ask, does this happen all the time? Can we get other shapes rather than this? Well, let's try it with different types. Well, this is just another explanation of that. 2, 3, 5. And then that is 2, 3, 2, 5, 3, 5. What they share is 2, 3, and 5. At the end, we get the null set, which is nothing. There is nothing in this set. That is a general way of putting it as A, B, and C. This is what we call a power set, which consists of consisting of A, B, and C. Arrows shows which sets are also subsets of another set. So this is a power set of 3 elements. Group theory is about the visualization of abstraction literally on a page or on the board. We would reason with it so we can invoke more kinds of intuition. An example of it is the geometric intuition, which we all share as humans. Now I would like to discuss the history on the foundations of maths. Well, foundations of maths were tried to be stabilized by set theory. Set theory was developed in 1874 by Cantor. Set theory is based on memberships in a set. On the other side, category was developed in 1945 by Mr. Eilenberg and MacLean. This was based on relationships in sets, so it was a continuation of set theory. Set theory also defined equality based on intrinsic characteristics. So if you're in the set, you are. If you're not, you're not. That would be your definition. But in category theory, sameness is based on roles played in context. Also, a set consists of some objects in set theory. But in category theory, a category consists of some objects and some relationships between them, satisfying some axioms. But the important thing to take from here is how set theory and category were different in defining equality. One on characteristics and one on roles placed in the context. I think there is a valuable lesson to learn from here. Equality is not the same as sameness. Equality is based on the roles placed. If someone can play the role, they would be seen as equal. We see this in normal life, in daily life, while we discuss the equality between women, between female and male. But we should focus on the roles played in a context instead of literally sameness, because sameness doesn't exist, because if it existed, we wouldn't have 2 different words for it. Category theory has an extra dimension which we use to express more nuance than equations. You don't see much equations in category theory, but you would see nuance and patterns. Let us explore 2 rules in category theory and also group theory. First one is associativity and commutativity. We have came across these a lot in school maths, but it's good to look at it here again. We say that a plus b plus c is equal to a plus b plus c, but with different places of the parenthesis. Well, this only applies to that context. Also, for commutativity, we have a plus b equal to b plus a. Now, associativity is one-dimensional, whereas commutativity can be applied to high-dimensional concepts. For example, if you look at 2 objects on a table from different perspectives, you would see that nothing has changed about them. But if you change the places of the parentheses of the 2 things, imagine 3 things, if you change the places of them, then you would notice a difference between them. Well, an example of the importance of the context, I would like to talk about custard and mayo. For custard, if you mix egg yolks plus sugar and then you add it to the cream, You will not get what you get with egg yolks if you mix sugar and cream at first and then add it to the egg yolks. With mayo, if you mix egg yolk with olive oil, step by step, like drip by drip, and then you will not get the same as olive oil if you add small bits of egg yolk. Well, in commutativity, we get more dimensions and therefore it allows us and gives us more nuance. With two dimensions, we would ask, is this commutable? But with 3 dimensions, we can ask, in what ways does this commute? And we can go until infinity. And there has been works which have been done on higher infinity, infinite category theory, which studies the relationships between the relationships. So I hope you can see by now that abstraction has a point. We gain a broader perspective. We deepen our understanding and we find out about more connections between things. And also we can understand the wider applicability of abstraction. But this was not the reason why I was attracted to category theory at first. We always go on talking about how useful some things are, and this makes us forget the joy that we get from fulfilling our capacity of doing such a powerful act. Now, a question I would like to address is, what can studying these relationships teach us about the nature of reality? I would say that we would see that everything is relative, and understanding that relativity, not just because of Einstein's general theory of relativity, that might have affected it too, but well, that could enable us to be more flexible in the world. For example, we can see Roger Penrose. So Roger Penrose has a triangle, which is a mysterious triangle, showing 3 different worlds. One is the world of consciousness, one is the Platonic world of mathematics, and one is the natural world. These 3 worlds are mysteriously connected. We can see that our consciousness has the ability to connect to the Platonic world of mathematics, a world with no time and space, with certain logical rules which have to be applied, otherwise they would not be a part of that world. And also, we can see the applicability of mathematics into the natural world. That is another connection. And also, our human intelligibility of the natural world is also another mystery. So these 3 things, consciousness, world of mathematics, and natural sciences, are mysteriously connected in a way which is a gift for us to be able to recognize and explore. The aim of all of this is to put everything there is into one thing, and putting disparate things they look different, and putting them together in units via their relationship, so you can then move them around your brain and make connections between them, and your brain would be able to function and understand it more clearly and effectively. For example, when playing Western classical music like piano, you don't read each note, just like when we read texts. Hopefully, we don't read each letter individually, but that because it would take a long time. But we would read the word and then read the sentence and then read the whole paragraph and therefore a page. The first step of learning how to read is to learn to group things together, turn letters into words and turn those letters into sentences, as I said. So to play a big piece of music on the piano, you have to group notes in chords and then those chords into phrases and those phrases into structures. Connecting them and finding a relationship between them shows us a clear path of trying to understand the fundamental structure of that. Category theory can also be applied into other fields because abstraction is widely applicable. This is because category theory is perfect for constructing a framework for understanding structure. And as I said, our world is structured and complex. So, using category theory, which is one of the highest abilities of humans, we would be able to understand how structure composes with other structures and also understand how we can transfer things to different contexts and maintain their structure, like the AI language that I talked about. It is also like sticking puzzles together and putting them together to make a bigger piece. This structure helps us develop our ideas further and explore how the fundamental parts of a system work together. And in the end, I would like to say that exploration is much more important than getting the right answer, especially in maths. Because it is an abstract world, you can create it easily, and if it doesn't hold, if the fundamental parts of your system, your mathematical way of puzzling out and modeling, is not correct, that world would fall, but it wouldn't physically hurt you, and that's why there's no reason to be afraid of it. It's just a perfect opportunity to get involved and delve yourself into, and also be able to enjoy a bit of order and certainty. And that's it from me this time. I hope you enjoyed my talk, and I hope I've been able and managed to show you a small property of our wonderful world that we live in. I would just like to mention that most of the topics, most of this top, my understanding of this topic was taken from a book called Joy of Abstraction by Eugenia Cheng, which is a perfect opportunity if you want to explore this idea further. And also, I would also recommend an article, a very short article, it's about 9 pages, by Wigner, Eugene Wigner, which is about the unreasonable effectiveness of mathematics in describing the natural sciences. Those would be perfect to explore this idea further if you would like. And thank you all for staying until here if you have. I hope you enjoyed it, and see you next time.